Hello and welcome everyone to the final episode of our mini-series, Sections in the Spotlight. Joining me today, I have not 3, but 4 illustrious leaders of our sections. Before I hand the stage over to them, though, I have a few quick housekeeping announcements to make. So let's get started. First of all, a few tips for those of you who might not be familiar with Zoom's webinar mode. Of course, it does have a chat box similar to a normal Zoom meeting. It's what you've been using to introduce yourselves just now. But next to the chat box, you should see an extra button labeled Q&A. The Q&A button is your friend. You can use that button to type in questions for any of our presenters at any point during the webinar. Please feel free to submit as many questions as you would like. And don't worry, when you submit a question, it is not going to interrupt the presentation. After each section has had an opportunity to present today, we will host a group Q&A and try to answer as many of your questions as we can get to in the time we have available. Also, one other button which you might see down at the bottom of your Zoom window is the Show Captions button, or CC. If you click on that button, you can enable or disable Zoom's automatic closed captioning. I'll let you decide whether it's more handy or hilarious. This is the final webinar in our section mini-series, which means that we're returning to our regular programming next month, and we are going to start with a bang. That is with the AAVSO Snooze campaign webinar. This one will be presented in tandem by Dr. Alec Habig and Dr. Bert Pablo, and they will go over everything that you need to know about the AAVSO's exciting project to monitor potential supernova progenitors. So, please do consider joining, and I hope to see you there. If you'd like to read some more about the webinar or to go ahead and sign up, you can visit our website at aavso.org/webinars. Also, I have a special announcement, which is that our 113th AAVSO annual meeting will be held this November at the U.S. Space and Rocket Center in Huntsville, Alabama, which is probably one of the coolest places on Earth. We are planning to have an opening reception in the same room as a Saturn V rocket to kick things off, and then 2 full days of scientific programming and exciting lectures on the topic of variable stars. We are accepting abstracts for presentations, and we are also looking for people to present posters. If you would like to learn more about the meeting, find out some information about registration, and join us, you can visit our website at aavso.org/113. All right. I would like to thank our 2024 series sponsor, Boyce Astro. The Boyce Research Initiative and Education Foundation provides online astronomy education, observatory resources, and research experiences to students, student teams, and schools in order to learn how to perform observations, conduct research, and publish their results in scientific journals, such as the Journal of the AAVSO. Please check out their webpage to learn more about their work. Okay, back to the webinar at hand. Now, before I hand things over to our section leaders, I would like to give a little bit of context on the AAVSO and its section system in general, because I know we have many people here today who are maybe not so familiar with what an AAVSO section is. So let's begin with an introduction to the AAVSO. The AAVSO is the American Association of Variable Star Observers. We are a long and historied organization, and our mission, which we've been serving for 113 years, is to enable anyone, anywhere to participate in scientific discovery through variable star astronomy. This mission has attracted a lot of fine folks, including observers, people who collect data of variable stars, and analysts, people who prefer to do data mining or reductions to perform studies with the observer's data. We have people of all experience levels, from those who have only just heard about variable stars a couple months ago, and they're just interested in learning more about what's out there, and those who can be mentors to those people who have been studying variable stars for 60, 70 years even, and are now happy to share their expertise. We have an active mentorship program that serves both of these people. We are all united by one thing, and that is that We all love doing science with the sky. As far as observations go, we have a wide range of capabilities and types of data which we collect. Perhaps the oldest form is visual observing. So some people actually don't even use optics at all. They just go out on clear, starry nights, look up at the sky at the brightest variable stars, and make estimates that way, contributing to the record on our brightest stars. On the other end of the visual observing spectrum, we have people who use very large telescopes like Roger Call here, and who make their visual estimates using an eyepiece that way. We also have people who use more advanced CCD and CMOS detectors and large observatory telescopes in order to do photometry or even speckle measurements of binary stars. And we have people who do what they can as they are able. Like here we have a solar telescope built by AAVSO on the right, which is just ingenious. AAVSO was able to contribute to our sunspot record of historical sunspot counts throughout the ages using this homemade telescope. Here's a slide that gives a summary of the AAVSO by the numbers. We are a pretty good sized organization with about 1,200 members, 800 observers, and 200 volunteers. And those categories are not necessarily all included because you don't have to be a member in order to be an observer or a volunteer. So we have a large community that we serve around the globe. We do this on a fairly small budget of $1 million per year and a staff of 6 people and 3 contractors. We have our public outreach programs that we run, such as this webinar series, educational choice courses, which provide a more college course style introduction to various topics in variable star astronomy. There's the mentor program, which I mentioned, our observing manuals, which we've written to detail different ways of contributing to science. And all of this pays off in that we are frequently cited in the scientific literature. In one previous survey, we found that 380 publications per year were citing the AAVSO or mentioning our data. We run a number of databases that we provide to anyone who's interested in conducting research on variable stars. There's the AID, which is our primary photometry database. We also have a spectroscopy database, AVSpec, which you might hear a little bit more about later today. Our variable star index is the go-to location for finding out metadata about variable stars, their types, their periods, such like that. We even have an exoplanet transit database and that solar database, which I mentioned, tracking sunspot counts. And of course, we do have a number of activities going on throughout the year. In addition to our webinars, we have those annual meetings like our 113th, which I was talking about just a minute ago. All right, so coming back to our mission. We achieve our mission through many different activities: collaboration, strategic partnerships, education, data stewardship. And one of the driving forces behind all of these efforts is our section program. So what is a section? This is a question which I was asking myself when I first joined the AAVSO several years ago. I heard people saying, oh, well, you should find a section you're interested in and you should join that section. But section is kind of a broad word. What does that mean? It's very simple. If you've ever been in a hobby club, an astronomy club, which had a special interest group, sections are the same exact kind of thing. A section is a group of people who are all interested in the same facet of variable star astronomy and who join together in order to discuss that topic, in order to take data of their favorite kind of variable star, in order to conduct studies, just in general, explore their subfield. So the role of the sections within the AAVSO is to organize and to support these concentrated studies on specific classes of variable stars or specific modes of observing. In order to do that, they've been developing tools, techniques, and many of them are running monthly meetings during which people get together and just talk about what needs to be done, coordinate on research projects. The sections are overseen by a leadership team, and that includes 2 types of people. We have the section leaders, and we have the science advisors. They both play an important role in guiding the section and making sure that the efforts of the section's members are well spent. And sections are a very open part of the AAVSO. Anyone can be a member of an AAVSO section. You don't even have to be a member of the AAVSO itself. We welcome people of all types. So if you would like to join a section, you'll hear a little more about this later, but there's currently 2 ways to get involved. You can visit aavso.org/join-a-section, and there you will find instructions for joining the sections forum, which for many sections is the primary location where discussions are held, information is shared. If you join that forum, you will receive emails in your inbox whenever a new forum thread is created or a new discussion is going on, and it's a great way to stay up to date with what is going on in that section. Also, I would recommend that if you're interested in becoming involved in a section, which you hear about today, please reach out directly to the section's leaders, and they will help you find a project which you can participate in and give you information on the section's upcoming activities. In order to do that, you can visit aavso.org/observing-sections. That's the URL that you see on the right there. You'll be presented with a list of all of the AAVSO's various sections. And if you click on one, it will take you to that section's page, where at the very top, highlighted in bold, is the contact information for the section's leaders. Just reach out to these people. They're all friendly, great people, and they'll be glad to help you get started. And with all of that said, I'm going to go ahead and end my screen share here, and we will hand over the floor to our first section leader. This is HB Heinz-Bernd Eggenstein, who is the leader of the High Energy Network section for the AAVSO. HB, it's really great to have you here.
Yeah, thank you. I hope my voice comes across clear. So I'm Heinz-Bernd Eggenstein. Hello, everyone. I'm one of the 2 leaders, actually, of the High Energy Network section, which was established like in around 2000 with a focus on gamma ray burst afterglows and not much more. That was almost dormant for a while and was then reanimated in 2020 with a bit of a list of wider targets. Now we care about gamma ray afterglows, kilonovae, active galactic nuclei, and of course, if the next galactic core collapse supernova comes around, we will be interested in that. So Dave Hinsel is the other co-lead, and I guess arguably we are the smallest AAVSO section, but maybe I can get some of you to join us. So what's our mission? So we look for optical counterparts of high energy transient events, and those events can be gamma ray bursts, binary neutron star mergers, X-ray flares, neutrino events, like the one that will tell us about the next galactic core collapse supernova. So what usually happens is that these events will be discovered first by professional astronomers, and that is because by chance these high energy events either interact so violently with the atmosphere that they don't reach the Earth, so you need space assets to discover them, or they interact so weakly with our instruments that you need super complicated instruments to even detect them, like gravitational waves or neutrinos. So once the professional astronomers detect this, they will send out an alert via some special networks and services, and we amateurs can then pick up these alerts and begin observing and contribute to the science. But the catch is that for this to work, of course, you first need to subscribe to one of these networks and services. And I see that as the main mission of our observing section, to advocate and explain and educate about the ways you can connect to these networks and services. And we'll come to that a bit later. you don't want to wait until the next day when you read about an event in the New York Times or on CNN. So one such network is the GCN, Gamma Ray Coordinates Network, which is historically dealing with gamma ray bursts only, but later then covered all sorts of high energy transients. So and it is distributing these alerts from all kinds of space-based and ground-based observatories to everyone who is interested and who is subscribed to it. Most of the content is public. It's only a few that are kind of secret. And it's also a hub for exchanging follow-up observation results, both in human written form and machine readable form. So, but there are other projects that are professional amateur collaborations, like the one that I guess these days for amateurs interested in gravitational wave events and in kilonovas is a must. And this is the Kilonova Catch-up Project, which is a citizen science part of the Grandma collaboration. I just love this logo. There's been a webinar about this, and you can watch that and see what it's about. But it's really useful in that if there is an event, this project will provide, given that you before have subscribed and told them what kind of telescopes you have and where on the planet your telescopes are, they will then generate an observing plan for your telescope, and then you can also submit the images you take for them to process in a pipeline together with all the professional images they have. So for the next galactic supernova, I would ask everyone who has a telescope or to join the SNOOS, the Supernova Early Warning System. So it's just a click to get on this alert list, and that will make sure that when there's the next galactic core collapse supernova, you won't read about it the next morning, but you will get an instant alert because this is driven by neutrino detectors. It's sure that we did actually miss a few galactic supernovae in the last couple of 100 years. But we will not miss any more because we now have neutrino detectors which will detect these kind of events, even if they're happening on the far side of the galaxy behind a lot of dust. So one thing that is also a nice tool for us in the section is the Astro Colibri app. There's a web application of it, and there's the nice thing is that there's a smartphone app for it. So you can literally put this in your pocket, and then you can subscribe to certain kind of events, and then you get alerts when professionals are issuing these kinds of alerts. Okay, so that's pretty much the same that I told you last year. I want now to focus on some new developments since our last HEN webinar. So there's a new player. There's a new X-ray space telescope in space now, which is a cooperation between the Chinese Academy of Sciences and the European Space Agency. So the primary goal is to discover high energy transients and monitor variable objects. And we're already working with that on the Kilonova Catcher project. So this is an astronomer's telegram that is the result of joint professional and amateur observations of an X-ray transient trigger that was generated by the Einstein probe, I think even in the phase of being commissioned. So you might recognize some names here, like Josh Hamsch is somewhere here. So it's yeah, it's really something that leads to results that are interesting. There are also news for on the gravitational wave detector front, so to speak. The 3 big observatories, 2 in the US, 1 in Italy, have resumed their science run this year. And the big news is that the kilonova hunting season was extended. So originally it was planned to end the science run beginning of next year, and now it's extended into the middle of next year. So essentially we get an extra bonus of 6 months that we give the universe time to throw an interesting event on us, like the next kilonova, the next binary neutron star merger, which would only be the second such event observed in gravitational waves and optical, if we manage to get the optical afterglow. I guess any astronomy talk these days must include a request to observe T Corona Borealis, even though it's not a high energy network target. But it's actually a nice training target for rapid reaction. So we basically know that something will happen within the next month, hopefully. So yeah, you have to prepare for it. Think about your exposure times, how much storage you will need, and that is all. Once you have answered that are the same questions that you will need to answer for observing, say, the next galactic supernova. We also have a project that doesn't involve transients, and that is keeping an eye on red supergiants to build a light curve. And then, I mean, in the best of cases, one of them will go kaboom in, I don't know, a few decades, maybe a century, who knows? And then we have then we know what this thing did the decades or centuries before it did go kaboom. But there will be a separate SAMS webinar for that. So I think I don't need to explain that more about that. We will be thinking about whether we want to communicate in the future just over the forum, or whether we want to join other other observing sections in offering regular webinars. Now, as I said, we are kind of the smallest section if it's measured by participation in the forum, etc. So I'm not quite sure, but if we have reached critical mass for that, but I would invite everybody with an opinion about that to go to our forum, and I will open a thread soon about that and give your comments whether we need regular webinars, or other groups have also now a Google Groups email list, and maybe that's useful. So as a summary, please consider what we are doing at High Energy Network as your part-time astronomy activity. I mean, nobody expects yet when you're into exoplanets or spectroscopy that you now switch to high energy. No, this is something to just do your regular thing, do your exoplanets, do your long period variables, but please also have this alert systems primed and phone apps and whatnot. So that if something very interesting happens, you can switch targets and observe that. And this is in your own interest, basically, because you don't want to be that person that is confronted at a party with the question what you did when that famous transient happened, and you have to invent excuses or lies why you missed out on it. So I think that's all I have. Thank you for your patience. And,
Thank you, HB. Great talk. All right. So next, we will be going to Tom Calderwood, who is the leader of the Photoelectric Photometry Section. Tom, take it away.
Okay. Come on. All right. Why is it not? Very strange. Let me move this out of the way.
Can you minimize that one?
Okay, photoelectric photometry. In principle, anything that converts photons into electrons is photoelectric. But in the context of astronomy, photoelectric photometry has a specific meaning. Most people who are doing photometry these days use cameras with lots and lots of pixels, and they get a bunch of stars photographed all at the same time. What we are doing in PEP is known as single channel photometry. We basically have one pixel, one big pixel. We only look at one star at a time. It's a technique that goes back over 100 years and it still has a use. Here is a simplified version of a photometer. Light comes in and is either directed to an eyepiece, which is used to center the star, or to the sensor, which produces the electricity that drives a counter. A flip mirror chooses between the two of them. The sensor, for the most part, in our group is a photodiode. And a photodiode is considerably less sensitive than a CCD sensor. That's bad if you're trying to look at faint things. However, if you're trying to look at rather bright targets, it's an advantage. This is the instrument most of us have. It's made by Optech Corporation. You can see that it has the eyepiece marked, two-position filter slider. I've also marked the position of the counter. It slides right into your eyepiece holder. If you have a telescope that you use for other purposes, you can swap this thing in and out easily. It's very portable. You can even run it off a 9-volt battery if you want to, and it's simple to use. Now, this is the observing process we go through. We have a comparison star, the variable, and a check star, as it is called. The comparison gets repeatedly sampled during this sequence, and the variable and later the check star are sandwiched between comparison star measurements. And now I will unshare for a moment and let Lauren bring up a short video clip. Okay, so this is my telescope. The box at left there is a little Arduino computer that I use to automatically record the counts. So here I am, I'm moving the telescope to point to the comparison star. All right, then I go in with the fine adjustment, get my comparison star centered. Then with my left hand, I'm going to flip that mirror to the P photometer position. You would integrate in the real world 30 seconds, at least 30 seconds, but I'm just showing a very brief integration here. Then you move the telescope off of the star to the nearby sky, and you do the integration again, because you'll have to subtract off those sky counts from the star counts. All right, then we move to the variable star. Again, center the target in the eyepiece and flip the mirror and integrate. Move off the star and integrate. Then we'll go back to the comparison star. Center and integrate. Now, after we do the integration of the sky here, what you would normally do is then sample the variable and the comparison 2 more times, but we won't show that here. Instead, what's going to happen is that we'll go to the check star. Center in the eyepiece. Integrate. Move to the sky. Integrate. And then we'll go back to the comparison star after this to finish the sequence. Lauren, why don't we stop the clip here? All right, so that's how we work. And this is how the giants of photometry, people like Arlo Landolt and others, this is how they started out. Now, bad news, good news. Obviously, it's slow, all right, and it involves manual work. But the photometer is fundamentally simpler to understand and to use than a camera. And that means it's easy to get good results. Another feature, since we're repointing the telescope, we're not limited to working with a fixed field of view for the variable comparison or comparisons and the check. This is a big advantage when you're dealing with bright stars, because a bright star very often does not have a suitable comparison within a camera field of view, a CCD field of view. But that doesn't cause any problems for us. We deal with that just normally. Another thing, I said these are easy to use. Here are a couple of high school kids. In a single night, I taught them the basics of how to use the photometer, and they started getting data. The advantages from my point of view is that, you know, it's only need a little bit of equipment. It's easy to do, and for the brightest stars, this is the best way to go, in my opinion. Optech made, and I say made because they no longer make new ones, 3 models of the solid-state stellar photometer. The one on the far left is the photodiode unit. The one in the middle actually does have a photomultiplier tube. It goes much fainter. And the one on the far right actually operates in the near infrared in the J and H bands. Our users almost all work with the Cassegrain telescope. In fact, I think they all have a Cassegrain telescope. A Newtonian telescope really doesn't work. You need computer control of the mount, really, with a computer program that allows for user-defined targets. And then you get a secondhand photometer, which are available at various times and places. And this is what it looks like. the photometer hanging down there. This is a telescope in equatorial mode. The reason for that, what you can see here, where'd my marker go? Here's the back of the photometer. As you swing the telescope up and up, it's going to hit the base. Okay, so if you just put this thing into alt-azimuth mode with this, you would be restricted in terms of how high in the sky you could point. That being said, alt-azimuth operation is possible. We're only looking at the very center of the view. Okay, that means we do not care about field rotation, so you can operate in an alt-azimuth mount. The trick, though, is that this is a 9¼ scope. This is an 11-inch mount that leaves just enough room to slip a couple of Losmandy rails in between. And what I have done here is to jack the telescope up so that the bottom of the photometer clears the bottom of the fork. So it can be done. We have meetings on Skype. Actually, we're going to do our first Zoom meeting in July, where we discuss, what's going on. We have an observing manual that goes over really rather a lot of the details of how PEP works and how to practice it. We have had a choice course, and if there's enough interest, we could bring it back. But we can also do one-on-one training. Just usually by email is sufficient to get people proficient in the basics. An example of our targets: Betelgeuse, nice bright star. If you try pointing a CCD camera at it, you will quickly saturate your sensor in almost certainty. But the photometer, it's right in our wheelhouse. This light curve here shows the year before and the year during the great dimming in V and B band from PEP observers. And this is the V band, just the V band shown on a larger scale. You can see we've got one data point that's, this right here doesn't look so good, but otherwise it's a remarkably smooth curve. And this is contributed by, 5 or 6 different observers. In contrast, here is what the camera observers reported during that same period. And you can see that there's a lot more scatter. And part of this is simply because in order to avoid saturation of a camera, of a CCD in particular, you have to take pretty extraordinary measures to reduce the exposure, reduce the aperture, and that compromises your results. PEP data have been finding their way into the professional publications. Here's one that Andrea Dupree there on the far left, underlined on the far left, is at the Center for Astrophysics. We have been supplying her with data. She's been a long-standing researcher on Betelgeuse. This is actually some infrared data that got into a paper in Nature. Here's a more recent Betelgeuse paper. And here's one, we have an observer in the Netherlands, Erwin van Balligouch, who has been collaborating with Dr. Van Henderen on some yellow hypergiants. And we are continuing to work with these stars. Now, an interesting application, these red giant stars, they're very cool, which means they have lots of absorption features. And some of those absorption features are exquisitely sensitive to temperature. If you use specialized narrowband filters, you can monitor the depth of the absorption and thereby infer the actual temperature of the star. Richard Wasatonic has been, who was at Villanova University, has been working with these other fellows on following Betelgeuse. And this is a graph that came into their paper. In the gold here, you're seeing the estimated temperature, which you can see taking a tremendous drop. This is the V-band magnitude down to here. And one of the filters they use samples a part of the spectrum that is unaffected by absorption. This lets you monitor the actual luminosity of the star. And you can see that, you're seeing, a fair amount of variation here in V-band, a lot less in terms of luminosity. That means the energy output from the star is actually not changing that much. What's happening is in V-band, you're getting a tremendous amount of absorption as the temperature drops. And we have a couple sets of these filters. Something new coming up, Alpha Cygni stars, of which Deneb is the prime example. It's a pulsator. Its physics are not fully understood, and there are other bright Alpha Cygni stars out there, and we are going to start following some of them. And here's our mascot, Count Von Count of Sesame Street. 1, 2, 3, watching the counts is an important thing to do while you're taking data, because those counts are the most direct indication of if you're having problems. And you can reach me at tjc@cantordust.net.
Wow, very great presentation. Thank you, Tom. All right. So next up, we will be hearing from two of the leaders of the spectroscopy section. To start off, I'll hand things over to Scott Donnell. Scott, take it away.
All right, thank you, Lauren. I'm going to keep, because of bandwidth issues on my side, I'm going to keep my video camera off. All right. Hello, everyone. This is your introduction to the AAVSO Spectroscopy section. We're going to do it in two parts. I'm going to spend about 3.5 or 4 minutes just giving you an overview of the spectroscopy section. And then after that, I'm going to hand it off to Steve Shore, our science advisor, and he will give his thoughts about the value and role of scientific spectroscopy. So you can find the spectroscopy section from the AAVSO homepage, and then within the observing sections main page, as shown here. The spectroscopy section is one of the most recent of the AAVSO observing sections, and I'll have to add that I'm fairly recent as a section leader, having taken over just this past January from Lauren. But the spectroscopy observing section was established for the purpose of extending the scientific range of AAVSO education and research. What we intend to do in this section is to promote astronomical spectroscopy as a broader tool for the investigation of variable stars and to promote productive collaborations between the professional and the non-professional observers. So the leadership team for this section consists of myself as the section lead and Steve Shore as the scientific advisor. We conduct meetings on the second Wednesday of each month, which include presentations on various topics of interest and also group discussions as appropriate. Now, these meetings have a dual goal of instructing members in the methods for obtaining quality spectra and in developing an understanding of the physical processes that produce the spectra we observe. We have instructional materials available to section members that include a series of PowerPoint presentations currently in development on various topics, a reference manual, a collection of past webinars and other videos, the choice course in spectroscopy conducted annually by Steve Shore, and also copies of presentations from past meetings. A key component of the spectroscopy section is AV-Spec. This is the AAVSO's repository of variable star spectra. So this database complements the AAVSO's database of variable star photometry, the AID, and provides additional and significant insight into the properties of variable stars. So what this means is that non-professional spectroscopic observers now have the opportunity to contribute to scientific research using spectroscopy, as spectra submitted into AV-Spec are made available to professional astronomers for their research and publications. And as a quality assurance measure, all spectra submitted into AV-Spec are verified by the AV-Spec moderator. Finally, section members have additional resources such as the spectroscopy forum and a set of spectroscopy tools that's also in development to assist them in their journey to becoming an accomplished spectroscopist. So we provide the opportunity for section members to showcase their programs of observation and also provide a list of recommended programs of observations for those who are just getting started. So this is my summary of the AAVSO Spectroscopy section, and thank you for your time. I'm going to hand it over now to Steve Shore for a few minutes to add his perspectives on spectroscopy as a scientific tool of investigation. Steve, take it away.
Thanks very much, Scott. Okay, so. Okay, so on the origin of spectroscopy as an astronomical tool, this is a cover of the Astrophysical Journal from the same year that the AAVSO was founded. And as the founding journal in the field of astrophysics, the idea was to apply the techniques that had already been pioneered in the laboratory in the middle and end of the 19th century to the study of cosmic objects. This opens up a whole new way of looking at physical properties of astronomical sources. But more to the point, it's the most flexible of the tools that we have in astronomy. So let me go through a couple of examples. This is really the birth. It starts out in the same way that it did with botany. That Secchi and Pickering, Fleming, Cannon, Maury realized that, and Vogt realized that there were systematics in the complexity of the spectra. They already knew that the dark lines in the spectrum were due to some specific chemical elements because those had been identified in the laboratory. But having a correlation between, for example, the colors of the stars and the complexity of the spectra, seeing that there were molecules or atoms in the spectrum and the different widths of the lines and the different lines that were present that were dependent on the ionization or the specifics of the medium led to, at the beginning of the 20th century, the realization, let's say, that you could use a spectrum to do not just classification, but actual diagnosis of the medium. And this was increased as a tool by Morgan and Cannan, who also realized that the broadening of the line, which is connected with a physical process in the atmosphere called pressure broadening, but that you could actually get information about the density of the medium, the temperature, the density structure, even the composition gradients. This is the other point, that photometry gives you the energetics of the medium, and it gives you a kind of rough characterization. The most important thing for variable stars is that it gives you the information about the time dependence of the radiative output. Since stars are bounded by nothing, the only way they can lose energy is by emitting. So if you can measure their total energetics, you have a window into their interior. But more important is that the light that's coming from that opaque surface that we call a photosphere has to pass through the outer layers of the star in the same way that light from the surface of the Earth, in passing outward through the atmosphere, gets absorbed and scattered. That information is all recorded in the spectrum. And you can see that, for example, with Vega, that if you use just the 3 classical filters of ultraviolet, blue, and visual in the broad band of the Johnson system, you see that all of the information, for example, in this middle portion of the spectrum, which includes several hydrogen lines, lots of metallic lines, all gets schmutzed into one single number. And so this entire spectrum, in this case, this is something like 5,000 pixels, is converted to 3 numbers. Now, to unpack the photometry requires that you use the spectroscopy. What you get is information in 3 primary categories. One is dynamics, because you've got the Doppler effect. That is, since atomic and molecular lines have specific wavelengths because of the structure of the emitting body, whether it's an atom or molecule, the individual wavelengths are perfectly known. So if you see shifts in the wavelength, this is exactly like having a speed trap. You can tell what the velocity of the medium is. At least you can tell the radial velocity. The composition, well, again, every absorber or emitter is going to have a unique atomic or molecular structure. And so it's an exact fingerprint of that specific contributor to the spectrum. So in this case, you've got the hydrogen lines from the Balmer lines, but you also have all of these additional lines. This is not noise. All of these are individual absorbers. They're atomic absorbers in this case. And this happens to be a spectrum of Vega. The third is that because you're looking through a medium which is partially transparent, it's exactly like having an Earth satellite looking down at the Earth in different filters. The spectrum integrates everything along that line of sight down to the last surface through which you can't see. So it's actually mapping the structure of the medium down to the last opaque surface. The dynamics, this is an example. This is a cataclysmic variable. It happens to be an old nova. It went into an explosion in 2013. What was observed about 5 years later. This is a trailed spectrum. It's about 50 spectra that are stacked on top of each other, where time runs in this direction and wavelength is across the bottom. And the individual lines, in this case, hydrogen, helium, and another hydrogen line, are varying in time. You can actually see here the movement of individual parts of the system, the hot spot in the disk itself, the companion, the irradiated part of the companion, moving relative to you as a radial velocity variation. This is over the course of one night. It's 50 spectra, each one taken about every 12 minutes. But in this, there are also lines that don't vary. For example, this is an ionized neon line. It's a forbidden line, so it's coming from a nebular environment, very low density medium, which is outside of the binary. This is the relic from the explosion, from the material that was expelled in 2013. These 2 dark lines aren't problems with the image. These are absorption lines from the interstellar medium between us and the source. And you see, they're not varying at all. So these provide an absolute frame of reference, at least as far as the radial velocity variations in this spectrum are concerned. So you see that you have three different components all in the same spectrum, these would be indistinguishable if one were simply to take an image of this, for example. You wouldn't see any structure here because it's just a point source. You might be able to resolve the ejecta, but in this case, it's very unlikely. And you certainly wouldn't see anything of the interstellar medium. The second is composition, that the fingerprint of each one of the contributors depends on its ionization state and its excitation. That is how the energy levels are populated within the atom or molecule. And so if you have an ensemble of these lines, you can identify what elements are present in a star or a galaxy or an interstellar cloud. It doesn't matter what you're looking at because the spectra are simply invariant. Okay, they're simply whatever the atom is. This happens to be a spectrum of a star which is almost the same as Deneb, which was mentioned in the PEP talk. That
Hey, Steve, we're 2 minutes to the hour.
okay. Finally, you can get structure, and I chose this one deliberately because RS Ophiuchi is a recurrent, just like a recurrent nova, just like T-Core Bohr. This is what you're going to see within the first week of T-Core Bohr. The bottom spectrum is another star, virtually the same type, that went off in 2010. The RSO was in 2021. Looking at the individual lines, these exceedingly narrow lines are coming from the wind of the giant into which a shock wave is propagating, like an atmospheric explosion. The broad line is the result of the shock itself. The narrow line is the ionization. So we're seeing here the variation in individual parts of the spectrum of the whole environment. The bottom spectrum is just a comparison of two of the events taken. In this case, V407 SIG was in 2010. The difference between these two spectra is a mere matter of a week. And again, you can see a complete change in the structure of the spectrum, which tells you what the medium itself was doing. This is what it was doing. That is, the ejecta were giving you the broad line. You had the shock here and the ionized region here. Again, exactly as you would if you had an explosion in an atmosphere. So, to finish up, this is an example, just the beginnings of the kinds of projects that are possible with virtually any spectroscopic instrument. The important thing that I should add is an advantage in spectroscopy, that because one is looking at morphology and absolute wavelengths, the fluxes are not quite as important. One can work in some pretty bad environments, even with scattered light, in a way that you might have a problem working, you might face problems working in such environments if you were doing just the photometry, but it's synergistic. So all of these techniques, the photometry, the spectroscopy, the visual observations, are all part of the story in trying to understand what the structure of the universe is on this kind of scale. So I'll end it there.
Great talk. Thank you so much, Steve. And thank you to Scott for the introduction. Okay, so it's now we've got some time for some questions. I see that we've had quite a few come in already. I'll begin with this question from Aiden Zeng, directed at Steve and Scott of the spectroscopy section. Aiden would like to know, can I conduct spectroscopy with a one-shot colored camera, such as those ZWO cameras that have the broadband filters built in?
Yeah, as long as you have a spectrograph in front of it. It really doesn't matter what the detector is as long as it's stable, because what you're looking at, especially if you're working in absorption spectra, is something that you can normalize. So you take the broad emission and call that 1. And then anything that's absorbing is telling you what the column of that material is between you and the source. You can even do this if you're working on interstellar. So it really doesn't matter. As long as you can calibrate it out, you can use anything you want.
Excellent. Thank you. All right, so our next question here is addressed towards Tom. Tom, Bob Tracy is curious whether there's an alternative to the Optech devices for doing photoelectric photometry, whether that's a commercial alternative or even like a DIY design.
There are some alternatives. There are devices. The Optech photometers started coming out about 1980. There were some earlier photometers, photomultiplier photometers that came out earlier. I forget the names of them. They do exist. In terms of do-it-yourself, there have actually been situations where people took an old defunct Optech photometer, removed the electronics, and kept the mechanical package and put in their own sensor. And I can send you, if you still have my email or whatever, I can send you a write-up of how that was done. But in terms of new stuff available now, I mean, even professionals have largely abandoned PEP because they can do, they can do so much more with the cameras. We're really a niche operation going after the bright stars for which cameras are not well suited.
Okay, thank you. All right, so our next question here is addressed towards HB. HB Aidenzeng is curious about how long a typical high energy network observation session would last. How much time per night do you guys end up spending?
Yeah, that's a good question. First, probably you're not doing that every night. You're looking for alerts and interesting alerts, and that is not something you do every night. But if you do it, it depends a lot on the type of event. So let's say you get an alert from a satellite that has seen some X-ray transient, and usually those have a rather good sky localization, so you already know where to point your telescope to. So, and then the optical afterglows can be quite faint. So maybe you would typically, if you have a medium-sized telescope, invest like 30 minutes to expose, and then you check it. And if you're not seeing anything after 30 minutes, it's, I mean, probably hopeless and not that wise to invest another 30 minutes. And some of us actually work with rented telescopes, like from iTelescope, and of course that costs money. And so 30 minutes is a cool thing to invest. Now on the other extreme, let's say now comes in an alert of a binary neutron star merger, a kilonova. And that typically comes from a gravitational wave observatory. If you're lucky, you also get a gamma ray burst, but that's not, that depends on the orientation of the event. You might not get a gamma ray burst, and the localization is rather poor. So the first phase of that night will be to even find the event in the sky. So you have to tile the sky depending on your field of view, and then you're hunting for the event, and that can take hours only until somebody, professional or an amateur, says, well, I think I found something. And then other people will check that. And once you have found that, you will want to stay on that the whole night, basically from dusk till dawn, because this is such an important event. I mean, there has only been one other event seen ever, and that event has been observed in the optical 10 hours after the gravitational wave event. So we have no idea how it looks in the first 10 hours, and yeah, we would like to know. So you would stay on that for as long as you as you can. And for the next galactic supernova, you will get a trigger from the neutrino detectors. And because of the physics involved, it can take any time from between, depending on the star, which we don't know, from minutes to hours before even the event breaks out of the star and becomes visible in optical light. And you don't know that in advance. So you will also spend the whole night. And you, of course, you have to prepare of that in terms of storage, in terms of clothing, in terms of coffee supply, in terms of arrangement with your spouse and your employer and whatnot. So yeah, that's a range, like 30 minutes to dusk till dawn.
Great answer. Thank you. Okay, so this next question here is addressed towards Scott and Steve. So, Frederick Phil is curious about the very simple RSpec software and the star analyzer, which you see marketed online by Tom Field. How accurate are these and how useful are they for scientific spectroscopy? Can you use those, or do you need to have like one of the slit spectrographs that, for example, Sheliak and other companies make?
So yeah, let me address that, and then Steve can chime in if he wants. My approach to the slitless spectroscopy using the SA 100 or 200 is it has very limited utility as a scientific instrument, but it has great utility as a instructional device. So a great way for individuals who may be contemplating getting into spectroscopy. Not sure if it's, something they really want to get into, but would like to try it, but are not willing or able to plunk down, multiple thousands of dollars for higher end equipment. It's a relatively inexpensive way to get your feet wet, get some exposure to spectroscopy. You can get results almost immediately. And so that's the value that I see in it. The scientific value is much less so. And I think that if you're interested in doing significant science in spectroscopy, then you really need to move on to slit spectroscopy, either the full spectrum or high resolution spectroscopy. So that's my 2 cents.
Let me just share a screen for just a moment, okay? There's slitless spectroscopy. It's a laboratory lamp of carbon dioxide. The 0 order is here, and the first order is in this spectrum. This is what you're going to get from it. It's a wonderful way of getting a feel for what is visible in a spectrum. These are some other examples of slitless spectra. This happens to have been in a restaurant, pizzeria, that I was at. This is a sundog, which is a slitless spectrum produced by the atmosphere. You don't even need a star analyzer. Or this one, which is first and second order internal reflection and dispersion. Or this one, which is a halogen lamp in my living room. But you see that there's very limited information here. It was very important at the beginning of the 20th century for doing large fields. This was objective prism spectroscopy, and the original spectral catalog that was done by Annie Cannon and Wilhelmina Fleming, the Henry Draper catalog, the HD, for those of you who have seen that designation for star number, was actually slitless spectroscopy. It was a prism placed in front of a telescope, and the field was imaged through that, so you could get the morphology of the spectrum, but it's a classification tool, and only that. It has its value, but done with modern equipment, it is far more important to have the resolution, because you can't recover from the low resolution any quantitative information from this kind of data.
Thank you, Steve. And I have a short comment to add on to both of these excellent answers. Steve, would you mind sharing the very first image that you showed us of the carbon dioxide lamp? Thank you. So this is just, I think, maybe the most marvelous example I've ever seen of something which I noticed as a user of a slitless star analyzer and a slit spectroscope, the difference between them. This is a gorgeous spectrum, and it is contaminated by the computer keyboard. If you tried to profile this, you would have some signal from the keyboard behind the spectrum. What the slit gives you is it gives you control. It gives you control over the background and the reproducibility of the spectrum, so it's not contaminated by other things in the field. So yeah, excellent example, Steve. I just wanted to add that note because to me, that was something that when it clicked in my head, that I finally got the difference between slit and slitless, it was really helpful. So
No,
thank
that's
you.
great. And the one thing I wanted to point out here that would actually be really nice if you looked at, say, Orion, is that you would see the variation in the intensity of the lines as a function of position. So here you can actually tell that there are differences in the temperature between different portions of this lamp.
Oh, that is cool.
Okay, so you get an image of the structure, but the problem is it's projected against the background. So everything is in there, and the extraction of the information, as Lauren said, is really hard. This, by the way, is the best example of this really cheap grading. If any of you want to try making a spectrograph, just take a CD or a DVD that you couldn't care less about and cut it up and put a slit in front of it. And actually build a very nice little slit spectrograph with that and a couple of razor blades and a tube of toilet paper.
Yeah, great tip. That's a fun project for teaching people. All right, so we'll move on now to a couple of questions which are directed at Tom for the PEP section. So, Tom, Phil Yele is asking about what the definition of bright stars is when you say that PEP is best suited for bright stars. Where's the magnitude cutoff?
I generally tend to keep the group focused on stars sixth magnitude or brighter.
Okay, thanks. Naked eye stars then. All right, and an additional question for Tom. So Michael Freeberg is curious about the effect of other stars in the field of view besides your target star. Don't you get contamination from all of those field stars?
We've only got one pixel. It's maybe an arc minute, couple arc minutes in diameter. The eyepiece certainly sees other stars in the field, but the sensor does not.
Okay. All right, thank you. All right. Now, a question for HB with the HEN section. HB, where is the equipment threshold for participating in follow-up on the kind of targets that you were talking about? What sort of telescope do you need?
Yeah, that also depends on the target, of course. For gamma, I mean, the most frequent ones would be like things like gamma ray burst, optical afterglows, and afterglows from unknown X-ray flares and whatnot. And those tend to be quite faint. So I would say, yeah, 8-inch and above. Opening aperture for the telescope. Yeah, the kilonova, the one we saw, the only example that before was like 16/17 magnitude. when it was seen 10 hours after the gravitational wave, but we think it kind of peaked around that, so that gives you an idea. And that was at 40 megaparsec. And since we haven't seen anything, a second event, we now believe that that was even quite lucky. So yeah, the next event could be like at twice the distance, or 1/4 the flux. So yeah, 16th magnitude, 17th magnitude, 18th magnitude. That should be realistic expectations for that. Interesting case is next galactic supernova, when you get that event. Now, people tend to believe that the next galactic supernova, because a supernova generally, it outshines the whole galaxy, that it will be super bright. Like we know that when Betelgeuse goes supernova, we will be able to read a newspaper at night. And that's the thing that is on people's mind when they hear next galactic supernova. But we have to keep in mind that it's much more probable that the next galactic supernova will be somewhere in the galactic disk. And not, so it will be attenuated by a lot of dust. And there's a 50% chance that it's on the far side of the galaxy, right? Because, 50% of the stars are on that side. So there are papers who say that, with some reasonable probability, it might be like 10th magnitude, 11th magnitude, 12th magnitude. So it's not unreasonable to go after that with a DSLR, where you have a nice big field and a telephoto lens. But of course, most likely it will be in the galactic band. So yeah, you get a lot of crowding there. So yeah, but yeah, you can still try with. If that happens, that alert, we will. Everybody with a telescope will look at it. And so yeah, that will be big fun, and you shouldn't be scared away by having a small telescope or having a huge telescope. Just go after it and try to see it.
Hear, hear. Thank you, HB. Okay, so now back to Scott with a question about spectroscopy. Rod Hughes is curious whether there's any plan in the works right now for a choice course on spectroscopy.
Well, that's a good question, and it looks like Steve Shore, who would be conducting that choice course, has had to move on, has dropped from this call. So I don't know. Earlier this year, Lauren, after I took over from you in January, I did pulse Steve about if he was planning on doing a choice course. He indicated that he would do one if requested. But maybe Brian could chime in. At this point, I don't know what Steve's intentions are with respect to the next choice course.
Mhm.
Yeah, hi Scott, just joining in from the ether that I was in the background here. I know that there is actually a spectroscopy choice course scheduled for this year, but I don't remember the exact date. I think it was planned kind of like in the November, December time period, but I don't know if it actually it was formally scheduled. So I would just say keep an eye out on the AAVSO choice course page. Or if you have any specific questions, drop a line to aavso@aavso.org, and we can try to let you know a more specific date once it becomes available.
Thanks, Brian.
Thanks for the input, Brian. Okay, another question for Scott. So Scott, Melanie Krausen is curious about the spectroscopy requirements in order to study those Alpha Cygni stars, which I believe that Steve had brought up during his presentation. Do you know anything about the ideal like if there's people out there who are going to be recording spectra of Alpha Cygni stars in support of this project, what wavelength regime should they be looking at? What resolution? Do you know anything about that?
I don't. Honestly, I don't. I would need a little bit more to go on. With respect, the unknown physics of Alpha Cygni stars. What unknown physics is Melanie referring to specifically?
Melanie, if you would like to specify a little bit further about what you're curious about, feel free. But what I will add just from what I've read, which I'm definitely not an expert on these Alpha Cygni stars, and I'm not quite sure what the open question is myself. I was a little bit distracted behind the scenes collating the questions when Steve was presenting. But I do know that in general, these Alpha Cygni stars often have interesting hydrogen alpha line profiles where you see temporal evolution in the, there's a P Cygni profile from the wind from the star, and it's quite weak compared to, say, luminous blue variables with their classic P Cygni profiles, but it does change fairly rapidly. Even Deneb, sometimes you'll look and it's all absorption, sometimes you'll look and there's a big emission spike rising out of the redward side of the wing. So I'd say high resolution observations of hydrogen alpha are never going to hurt.
And Lauren, if you specifically mentioned essentially a circumstellar shell as the source for the H alpha, and if that's the case, then I agree. And if that's what if that's what Melanie was referring to, the unknown physics, then I think we've answered the question, but still would like to find out if she had something else in mind.
It looks like Melanie's in the chat, and that is what she was asking, so that's great.
Okay.
Thanks, okay. Let's see. There's one more question here, and this one's addressed to me. Okay. So this comes from Jeff Jenkins, who is curious about some of the stuff that I talked about previously with my own spectroscopy using a star analyzer slitless grading on a Dobsonian. And Jeff is curious whether I was using the 100 or the 200 along with my prism. So Jeff, I was using actually both, not at the same time, but I would alternate depending on what sort of targets I was going after. If I was working on the brighter targets, I'd usually use the Star Analyzer 200 because that would help me get a higher dispersion with the amount of spacers that I had available and minimize the vignetting, because while technically you can increase the dispersion by adding more and more spacers, you will eventually run into severe vignetting if you keep doing that. So I would use the Star Analyzer 200 on the bright stars, Star Analyzer 100 on the dimmer stars when I didn't need as much resolution and I was more concerned about just raw flux. So I hope that answers.
And Lauren, if I could kind of add to that too, my general understanding is that the SA200 would be the filter of choice if your intention is to mount it in a filter wheel that is relatively close to your sensor. So the SA200 works better when you have kind of a closer proximity to your sensor, but the SA100 works very well when you have the ability to space it appropriately at the appropriate sensor to grading distance. Yes,
absolutely. I think that's the reason why the Star Analyzer 200 was originally debuted, even was for use in filter wheels. It's got a lower profile housing to help facilitate that as well. So thank you for adding that. Okay, it looks like we have come to the end of our Q&A. So before I put up the closing slides, I'd just like to remind everyone some of the things from my introductory presentation. Specifically, if you are intrigued by anything that you've just watched today, if one of these presentations really spoke to you and you want to go get involved in that section, you can. You can become a part of these projects. To do so, I highly encourage you to go to our website, aavso.org, and you can either, from our homepage, which actually, I guess I should just screen share this real quick and show you guys. That would probably be the best way. From our homepage, you can access our list of observing sections. So here we are on the AAVSO's beautiful landing page. Scroll down a little bit. This tic-tac-toe grid over here, observing sections, click on it. Here is your list. Here are the observing sections which we currently have active within the AAVSO. Click on the one which interests you. I'm totally not biased when I click on spectroscopy. And up here towards the top, you'll see the leadership team, the lovely people who have just presented today, and contact links. Reach out to them. Let them know that you love their presentation and that you're interested in becoming involved and you want to help with the section. And they will help you find ways to participate in the meetings, the programs, and the projects. All right. Now let's go ahead and put up our closing slides. Okay. I believe that's screen sharing now. Hopefully, maybe. Can you see my slides?
Not
no,
quite yet.
It says that the screen sharing is paused. That's interesting. All right, let's try one more time. Zoom and its quirks, you know?
There we go. Works now, Lauren.
There we go. All right, thank you. All right, so first and most important, I would just like to extend a heartfelt thank you to HB, to Scott, to Steve, and to Tom for their excellent presentations today. Thank you guys. This has been wonderful. I would also like to thank our 2024 series sponsor, Boyce Astro. The Boyce Research Initiative and Education Foundation provides online astronomy education, observatory resources, and research experiences to students, student teams, and schools in order to learn how to perform observations, conduct research, and publish their results in scientific journals, such as the Journal of the AAVSO. Please check out their webpage to learn more about their work. As a reminder, coming up next month, we will be airing a special webinar all about the AAVSO's ongoing snooze campaign. This ties in directly to what HB was talking about during the High Energy Network section presentation. It'll be presented in tandem by Dr. Alec Habig, who is the PI of the Snooze Project, and Dr. Bert Pablo, who is our very own staff astronomer and is the PI of the AAVSO side of things. It's will be airing on July 13th. That's a Saturday at 2 p.m. Eastern Time. If you'd like to learn more about the webinar and go ahead and sign up, please visit our website at aavso.org/webinars. There'll be lots of high mass stellar supernova progenitor talk on tap, so please do join us. I have a special announcement about the AAVSO's annual meeting, namely that this one's going to be held at a rocket center. And guys, that is awesome. So go sign up. You can find out more about the meeting on our website at aavso.org/113, because this is our 113th annual meeting. And yeah, we're in for a good 3 days of science and rockets and camaraderie with all of our fellow variable star observers. I hope that I will see you there. All right. Now, today's webinar has been recorded. And if you would like to check out the recording, you can do so on our Facebook page, where it will be automatically uploaded just as soon as I close down the webinar here. Also, within a few days, we'll have it uploaded to our YouTube channel, where it will join an enormous library of educational webinars just like this one, including some of the earlier ones which were referenced during our section's talks today. You can find our library on YouTube by visiting YouTube and searching for AAVSO HQ. That's our username. All right. Before you log out of today's webinar, or when you log out of today's webinar, you should be redirected to a survey. And I would really appreciate it if you could take a couple minutes and fill out the survey. Let us know what you thought of today's webinar and perhaps what you'd like to see out of section webinars in the future. This is the end of this month's section mini-series, but it will not be the last time that we will be hearing from our sections about their activities. So yeah, we can't wait to hear your feedback. Thank you, everyone. And with that, I would like to extend one last heartfelt thank you to Heinz-Bernd Eggenstein, to Tom Calderwood, to Scott Donnell, and to Steve Shore for their excellent presentations today and for all of the work that you guys do to run our AAVSO sections. It's really impressive what you've managed to achieve, and we are so grateful that we have you as our volunteers. Thank you. All right. See you all next time.